Okay, let's start with a couple of administrative notes. So as you can see, and as you know, we're in a new room. We have more space. Yesterday, I approved a bunch of foresads, and today I sent out an email to everybody who was on that batch. I found out there was one person at least who was not on that batch. For some reason, I didn't get their request, like didn't go through the system. So is there anybody here who did not hear from me about your foresat? So you've still not been foresated. 1, 2, 3. And you're certain you have submitted before. Okay. So here's the thing. I would just say, we'll take care of it, but today's Monday, and that's the last day to add last day. Actually, Z, can you comment? Don't know why. I just want to ask you, you were one of the people who was not on your form was somehow not processed in the foresat batch, right?
So it's already added inside the class.
You were already added?
Yeah.
Okay. For some reason, I didn't get your email, so maybe you guys will also.
Okay.
But I would follow up like tomorrow. I'll ping, if you can give me your names, I'll ping the admins, folks as well, if you can stop by at 3:40 Whitmore to check the status of the Okay. But in any case, we have, as you can see, we have space, so we should be fine. Anybody not on Scholar yet? You're not on Scholar. Do you not have access? You couldn't add the website yourself.
Actually, I didn't try it, but I'll try it.
Okay, try it. If that doesn't work, that's resolved. Anybody else who's not yet on Scholar? Okay, perfect. Okay, so administrative things done. The reason why Scholar is important is what I'll do is I'll put the slides on Scholar, and I'll also post. So what I usually do is I come out, just before coming out, I write down a couple of notes. This is stuff that I'm going to write in class, this stuff I write. In previous years, what I've done is I've handed it to a TA and we've sort of scanned it and put it out. So you have my notes, which means if you'd like to sit back and listen, that's fine. If you think you'd like to take notes just to keep along, that's fine as well. There is a public website of the class. That's the public website. What I'll try to do is, you'll have all the deadlines here, and what I'll try to do is I'll post some videos or side readings. Some of them will be marked optional. I often find personally that some of these lectures are extremely interesting. If you'd like to follow them along or for the various topics, you're welcome to. Okay? Alright, so that's about that. Okay, another random trivia. If you're interested in the areas of computer vision and machine learning, there's a reading group that happens in the EC department. It's open to everyone. It's not restricted to EC. Happens Friday, 5 to 6. And if you just Google for computer vision and machine learning reading group Virginia Tech, that should be the top link. You should be able to find it. What we usually do is read computer vision and machine learning papers from conferences, recent conferences. All right. So. Any other logistical? Yes.
Where does that reader meet?
Oh, sorry. Whitmore 4. I'll put it here because I'll upload these slides. So 654, 657, 657, 654. Thank you. All right. So it'll be there. Okay. Any other administrative questions or anything? Okay. So then let's get started. Arjun, can you hear me in the back?
Yeah.
So here's what I want to cover today. Last time we talked about different kinds of machine learning problems. Today we want to go over a specific kind, which is supervised or inductive learning, which sort of tell you the high-level setup. We'll talk about sort of what is a classification problem, what is a recursion problem. We'll talk about procedural view, statistical view, and we'll talk about how do we measure performance. The goal today, and if we can get to it, we'll see your very first classifier. This is stuff that you would code up if you did not come to a machine learning class. This is the simplest thing that you can do and still call it a learning algorithm. You sometimes have to put learning in quotes, but it still works. If we can get to that, that'll be good. But one of the things that I want to do is I want to define a framework, because supervised learning is something that we'll spend a majority of this class on. So what I'd like to do is sort of list down certain notations, certain names, so that we're all familiar with it, because we'll see it over and over again in different outputs. Okay, so just to remind you, this is what we talked about last time, that there's a few different types of machine learning problems. There's supervised learning, where when data is given to you, you get input and the desired output that you'd like to see, so X and Y, and so you have supervision at training time, and we'll define each one of those terms today. There's unsupervised learning, where you're not given any desired label. All you're given are some just raw data X. You're not told what we'd like to map this X to. You have to just figure out what is X similar to, or can you cluster X, those sort of problems. And of course, in between the two would naturally be weakly supervised or semi-supervised problems, where you have a subset of the data which is annotated, a subset which is not. And we talked about reinforcement learning, where you make a series of actions or decisions. So let's get started with the supervised learning problem. So here's sort of the high-level, big picture view of what is supervised learning. You're given examples of some function. So I tell you X, and I tell you there is some unknown function that you don't know, and I tell you what the value of that function at that point X is. So you're given these pairs, X and f of X. And what I ask you to do is predict this function value on new examples. So tell me what f of X will be for some X that you have not seen. Okay? The reason why this is called inductive learning is if you compare deductive reasoning with inductive reasoning. So deductive is sort of top-down. You're given a set of rules, A implies B, B implies C, and you sort of infer that if A is true, then C must be true, right? So that's sort of a top-down reasoning. This sort of reasoning is sort of bottom-up or inverse type reasoning, where I don't give you any rules. I give you certain things that are known to be true. I tell you what X is, and I tell you what f of X is, and what you're asked to infer are relationships between X and f of X. What could that be? Okay. There's a couple of different types. We looked at this f of X. If the output Y is supposed to be discrete, we'll call that a classification problem. This is the classifying email X into spam, non-spam. If it's a continuous mapping, then the output is continuous, and we'll call that a regression problem. So for example, one particular problem that, let's say if you're the company Zillow, you're extremely interested in, if I know something about a house, I know the address, location, size, various attributes, can I predict its market value or price? Can I predict what it will sell at? That's a continuous value output. Okay? And so f of X in that case is a continuous value thing, and that's what we'd like to do. We don't know what maps the attributes of this house to the price, but we'd like to discover that. If f of X is probability, this is going to be a third sort of class that we didn't talk about last time. If somehow what I'm asking you is, how likely is it that I stumbled upon this X? What is just the probability of coming across a patient walks into a hospital, he's exhibiting symptoms A, B, C, and D. How likely is this? I don't want to know whether these symptoms mean cancer or non-cancer or tumor or non-tumor. I just want to know, is this something that could happen? How likely is this? And you could see that predicting probabilities is a kind of regression problem. It is a continuous variable, but it's a very special kind of continuous variable because it's probabilities, so that between 0 and 1, they have to sum over the space of whatever domain you're talking about. So it has its own sort of special constraints. And so often it's studied as a separate problem altogether. Okay. All right, so here's a quick little thing. We talked a little bit about this last time, but when would you like to use supervised learning? Here's a couple of reasons where you would want to use supervised learning. So X to f of X, why would you want to write a machine learning algorithm to do this? One situation where there is no human expert. I cannot go to a human, and that may be a problem like binding for an AIDS protein disease molecule. It may be a problem where the humans can perform the task, but they can't explain how they do it. So I can go to a human, I have this black box, I can feed them an X, and they can tell me what f of X is. I can give them an image, and they can tell me whether it contains a face, but you can't really tell me how you do it. If you look at it, and you just sort of know whether you're looking at a face or not. So we can get these samples, but we don't know what that mapping is. Or it could be a situation where the desired function changes frequently. In this case, the stock prices for the last 10 days. There may be people who claim expertise on this. That expertise is questionable often, but even if you claim expertise, even if we do have human experts, even if they can write down, here's why I believe this, that may be changing. And so what you'd like to do is have an algorithm that is continuously updating itself without having for you to go to a human expert. Or it could be a situation where a user needs a customized function. So every, F is different for every one of you. What is spam or not spam depends on what person I'm talking to. Some people like much more restrictive settings, some people are much more okay with variables. So one man's spam is another man's information. Okay. So last time, let's talk about this. Last time we went through this slide, and what I'd like to do is drop up the slide and define a little bit of notation that hopefully will stay with us as the class goes on. So. This will happen a lot. I do a mix of slides and notes, and so my ideal classroom is one in which there's a projector on one side and a board on the other side. I never find that, so every semester you'll see us doing this. Okay, so here's the sort of notation that we're following. So I'll use X always for the input. This is sort of what will stay consistently as input. If I'm writing in LaTeX, I tend to make things bold. I can't do that on the board, so I'll introduce vectors with the arrows. Okay, so I'm going to use X with that arrow on top to mean that it's actually a vector. It lies in some real valued space already. Okay. Sometimes X is going to be a discrete variable. So sometimes the kinds of things that we'll measure are discrete things. So if I go to a house and I ask, does this house have, internal heating? Or every house has internal heating, but some binary thing like that. In that case, this can be a discrete input as well. Right? So it can be 0 or 1. Okay. This will always be input. Often in machine learning language, these are called features that we extract from the data. If you're talking to a statistician, they will often call them attributes. Doesn't really matter. For our purposes, this is going to be features, feature vectors, input, whatever. How are you representing your input? Right? What does input come in? That's always input. I'll use Y as always the output, and sometimes I'll use Y hat for the predicted output. But this is always my variable for output. If we are solving a regression problem, a one-dimensional regression problem, then Y will be a real valued variable. So that's regression. If we're solving a classification problem, then Y may be something like for binary classification. Okay, this is going to be important. Can the people in the back read that? Should I stop writing at some point?
Yes. Yeah, I think this is also fine.
This is good? Okay, I'll try to stop somewhere here. Okay. So if your output is 0, 1, we'll call that a binary classification problem. This is a 2-class classification problem. Email to spam or not spam. If it's a multi-class classification problem, then Y will belong in 1 to some discrete set. All that. Multi-class. Okay. All right. And I'll admit up front that at some point in this class there will be a little bit of confusion, because we will have to distinguish between a vector X and there will be x1 to xn, many such vectors. And sometimes I will talk about the ith dimension of a particular vector, and so it's going to matter whether I write the arrow notation on top of it. And I will admit right now, there is the probability that I will mess up at least once is 1. So I will mess up, but hopefully it'll be clear from context. Sometimes I'm talking about multiple vectors, and the subscript is indexing which vector I'm talking about. Sometimes it's talking about ith dimension. Okay, so far so good. The things we're going to be interested in are going to be mappings. So we're going to be interested in functions from the space of X to the space of Y. The space of inputs, images, emails, whatever, to the space of outputs, whatever, spam, non-spam, does the image contain a face, what is the price of this house, okay? And one thing that we're going to talk about is a set of such mappings. There's the one mapping that we don't know anything about. That's what produced. There's an unknown mapping. Whether an email is spam or not spam, what the true house price of a particular house is. We don't know what that is, but we're going to search. We're going to consider a set, and this is going to be a little bit of awkward notation. It's a set of G's where G's are mappings from X to Y. This is just, F is just something that takes an item X and gives you a value Y. G is a set of such things. Okay? A set of mappings. And that's when it's going to get confusing and problematic. Why are we talking about sets of mappings? Okay, let's bring this back. Okay, so input is X, output is Y. There is some unknown target function F that we don't know about. That's the true mapping. You can think of it as reality, whatever reality is that we don't have access to. And what we're trying to do is, we don't see F, what we see are samples from F. So we see X comma F of X, or in this case we've written Y1, right? So we see a data set like this. Usually in my notation I'll always use N, capital or small, for the number of samples, and D for the dimensionality. So N will always be the number of samples or data points, or inputs, and D will be the feature dimensionality. How many things are we measuring about the data? Okay, and we're going to talk about, as I said, this model or hypothesis class. These are mappings from X to Y. For example, if Y is classification, what we may do is take a weight vector and multiply it by that feature vector X. That gives us a score, and we threshold based on that score. This is what we did for the spam classification example last time. We took an email, we counted what words were happening in that email, we multiplied that by a weight vector, that gives us a score, and if that score is positive, we call that spam. If that score is negative, we call that not spam. I'm writing sign, which means Y is +1, -1, and we'll sort of work around that. Okay? So this can be one hypothesis class, if you want. Okay, and so learning, in some sense, all of supervised learning or all of machine learning then reduces to a search problem. It's an optimization problem. I give you a set of possible mappings. Forget what they are, whether they are dot products or whatever. There's a set here abstractly defined. That set may be infinitely large, that set may be exponentially large. Find me the best mapping in that set that fits my data and works. Okay, so that would be all of sort of supervised machine learning. Any questions so far? Okay, so here's one sort of picture that we'll often find useful. Up here is the unknown target function F. It generates, we don't see what this unknown target function is, it generates these training samples x1 through x1, y1 all the way to x and yn. There is a hypothesis set, that's the model class, it's the set of candidate mappings. And what the learning algorithm does is it takes as input this is a design choice that you as machine learners have to make. What is my model class? Is my model class, this is where all the keywords that you've heard come in. Am I using a nearest neighbor classifier? Am I using a neural network? Am I using an SVM? Am I using a decision tree? Or what algorithm am I using? Okay? And that is fed to a learning algorithm, which in this case would just perform a search or an optimization problem. It would check what is a good hypothesis member in this set that explains this data and works well on new data. Okay, so the output is going to be an element G, which is a mapping from X. Does that make sense? So far, so good. Yes.
So basically, you don't know what the mapping function is, but you give it like a list of possible mapping functions, and then you see which one works better.
In some sense, yeah.
So basically, it's at some point you can have like a list of mapping functions that none of them satisfies.
None of them work, yeah, or a bunch of them work, or something in between where some of them work, some of them really bad, and how do you then find it? Exactly. Excellent question.
But how do you choose your candidate formulas then? You have to know a lot about the inputs.
Yeah. So this is where where does this edge come from? How do I decide? How do think of things? Let's talk about concretely some problem.
Okay.
Predicting house prices, right? How do I know exactly what amount of information to gather about a house when I need to predict its price? The wisdom that is arriving more and more today, and that's this, what is X? Just gather as much information as you can. That's why we live in this age of big data. Just put in as many sensors as you can, measure the squared footage, measure whether or not there's, what kind of interiors they have, how many floors, what's everything that you can about this house. Create this really large vector, and we'll try to figure out which ones are important, right? And we'll try some class of mappings and hypothesis functions, and we'll sort of see which ones work better. Yes?
A little bit out of this thing, but I'm trying to understand here, how would you fit in the other parts which you said for supervised learning, as well as unsupervised, as well as the categories within supervised, within this whole scenario? So it's a big question, but still try to...
So think about it this way. So in unsupervised learning, first of all, there's no Y coming here, right? So you have to change your definition. Like, are we really talking about mapping? So you can talk about mapping. So for example, when we talk about clustering, we will talk about labeling a data point and providing it a discrete label of a cluster. Like, is this similar? Maybe emails come in 10 different types. It's an abstraction. Emails come of 10 different types, and I don't know what those types are, but I can sort of break this this set of emails into 10 different types. And so there you'll have to sort of pick some working Y. The hypothesis set will still, the space of edges will still work out fine. You'll have to change exactly how you do the search, because what is a good clustering will be different from what is a good labeling. And we'll talk about this in terms of the loss function. Like, how do you measure performance of these systems? That's a great question. Yes?
Does the way how you select the hypothesis set affect the final results?
Yes. It's going to, there's a really nice paper online about, how, I forget the title, but there's a little bit of black magic involved in machine learning. Historically, all the effort in machine learning has focused here. You get some data points, you decide some hypothesis set, and I'll really do a good job at this optimization. And there was always this sort of little black magic, like, how do I know, how do I represent images? How do I represent emails? How do I represent houses? And that was all sort of hidden away here. And things are changing. People are trying to do sort of end-to-end learning and trying to do, trying to learn what sort of space of functions that you should be working about. But it's a difficult problem. And give me a few slides. I'll show you an example, and you'll see why this has to be hopeless. This has to be really, really difficult to do. But we're able to do some of this. Okay. So if you step back, here's what the basic steps of supervised learning are. If you face a problem at your end, here's what you would usually do. If you have a problem that you're thinking about, the first step would be you would set up a supervised learning problem. You would go back, maybe you're working in aerospace, biology, whatever. You'll think about, okay, what is X in my domain and what is Y? What am I trying to predict? You'll start collecting data. Data collection is this process that we've all gotten really good at. The hard part is not connecting X. That part's easy. That's what you equip people with sensors for. The hard part is connecting Y, the annotations. Once you have X, you have to go to some oracle, or you have to go to some human expert and some labeler, and you have to get them to label all this data for you. Right? The next part is representation. Like, how do I represent my data? What is X? What am I measuring? I can't possibly feed in raw data, right? If it's an email, I cannot feed you a series of zeros and ones. It's a binary representation. You will learn. That's not gonna work. The learning and estimation part is, can we find the best? This is where sort of, if you had to think about machine learning as a black box, this is where it works really well. We know how to do this part really well. It's the model selection part, like should you be using decision trees or neural networks? That's what comes here. At this point, the algorithm is, if you're happy, stop. If you're not happy with the results, go back and iterate one or more of these steps. Okay, that's sort of what it'll do. Okay, so I claim that machine learning works in a lot of domains, and I claim that it shouldn't work. That it should be really, really hard to do. Here's a really simple example. So let's talk about. Let's not worry about continuous X. This is 4 things that I measure about something, right? And let's make life really, really simple. They're binary features. Maybe it's a house, and I'm just measuring some things about this house. 0, 1, 0, 1. There are 4 things I can measure. There's 2 to the 4 possible combinations of those 4 things that I can measure. There is some function that you're trying to learn. Let's not even worry about a regression problem. Let's make it a simple binary classification. Is this house going to sell in the next 1 week or not? Right? 0, 1s. And let's ask the question, how many such functions are there? Right? So if x1, x2, x3, x4, y is the mapping, the f of x that we don't know, how many such functions are there?
16.
Let's do the general setting. So general setting, x1 all the way till xd. Let's say I measure d-dimensional things, not 4, that's fine. Let's write out an entire truth table. It goes from 0, 0, 0, all the way to 0, 0, 0, 1, all the way to 1, 1, 1, 1. Okay, that's the entire truth table. There is some y, which is f of x, which is x1 to xd. How many f's are there? So
Would it be 32?
2
Sorry?
power d.
2 to the power n
Power
plus
d.
1?
2 to the power n. So there's
N-
no
n plus 1.
There's no n here. We have d-dimensional. Let's say d.
Two
So
power d.
d plus 1?
2 to the power d plus 1.
So
Why?
for every one you would have like 0 and 1, so for each one you would have 2, and then you have 16 inputs, which would make it 16 into 32.
Almost. So reasoning so far seems correct. There are 2 to the d rows here. Okay, in this table. Very nice. Every single element here can be 0 or 1. Every time you change an element, you've just changed f. It's a different mapping. So the number we're looking for is 2 to the 2 to the d. That's the total number of, that's the size, it's the hypothesis class h of g from this 0, 1 d-dimensional Boolean to 0, 1. That's this hypothesis class we're talking about. Right? Every time you do a mapping from d-dimensional binary features to 0, 1, you have this table. It has 2 to the d rows. Everyone can have 0, 1, 2 to the 2 to the d. Okay, that's a problem. 2 to the 2 to the d is a strong problem. It doesn't matter how many houses you sell if you're Zillow. You're not going to get that much data to know exactly. Let's be. See, every time you get a data, what happens? You take a row, you measure something, right? You get a data point, x1 to xd, and somebody tells you that this house sold. Okay, great. It's one row down. You measure something else, there's another row that you've seen, and this house did not sell. Okay, great. If you go ahead and you measure n such rows, you're still here. Even if I provide you n samples, there are still 2 to the d minus n rows that you've never seen before. You've never seen those configurations, and what I'm asking you is to tell me what could they be. Yes?
Isn't that 2 power d minus n? 2 power d minus n?
Not quite. So it's 2 power bracket open 2 to the d minus n. So here's what's happening, right? There's 2 to the d rows. There's n of them that get filled in. Let's assume unique data points, right? I give you n samples, they fill in these. So n of these are filled in. So I have 2 to the d minus n such rows to fill in. And I can fill those rows in with zeros and ones. Does that make sense? So that's why the n, and that's one of the problems, right? It subtracts here, it's still sitting, there's a big 2 to the n sitting here, you've just subtracted an n here, and this is still sitting in the exponent. The space of possible mappings is hopelessly large. It doesn't matter how much data you collect, you're not going to be able to, you're not going to be able to fill this table. And this becomes extremely complicated as you measure more and more things. You measure 2 things about a house, the table's already 2 to the 2, 4 rows. If you measure 100 things about a house, 100 features, that's not a lot in modern machine learning. You'd like to go ahead and measure thousands of variables about a particular thing, right? There's no way you're ever seeing that much data. So the sort of take-home message is it shouldn't work. Machine learning shouldn't work, and it's not going to work. There's a simple thing. If you don't make any assumptions, there's not going to be any learning. Right? The problem here is we're not making any assumptions. We're saying these rows could be anything. The search space here is hopelessly large. The search space is edge. And we just can't do a good job at that. You cannot search over that large a space. So no assumptions, no learning. Yes?
Can you make the assumptions like column-wise or row-wise?
Good question. So where do the assumptions come in? So you would sort of make the assumptions both ways, column-wise and row-wise. You would say, if d minus 1 of the features are the same and only the dth feature changes, chances are the function is not going to suddenly jump from 0 to 1 or something. Right? You'd have to make smoothness assumptions. Right? You'd have to say, if I think of this as a d-dimensional binary vector, if I look at all other binary vectors in some Hamming distance ball, then there's some sort of smoothness that as I change 1 bit or 10 bits away from you, suddenly the function doesn't just arbitrarily jump from zeros. There's some smoothness. Okay, so if you're not going to make any assumptions, there's not going to be any learning. Here's that felt a little abstract. Here's another sort of thought experiment that we can walk through. So are Klingons from Star Trek or Star Wars? Star Trek. Okay. So you're Captain Kirk. Right metaphor so far? Okay, Star Trek. So you land on a planet. On that planet, there are 2 languages spoken. One is Klingon, one is Mlingon. They're both languages that you don't speak. Here's my training data. You walk up to someone, he identifies himself as Klingon, somehow you're able to make that out. There are 3 words that he speaks. Click, school, who. Then you walk up to someone else who identifies himself as Mlingon, and that's like, ma, mu, ma. Okay? You don't speak the language, that's your training data. You've just seen 3 words, and here's testing data. I just give you a new word, and that's cop. And my question to you is, which language is this? Okay, so let's pause before you make a guess. This is what supervised learning feels like to an algorithm, if I were to sort of give it feelings. Right? To us, when we look at images, we have extremely heavy priors. When we look at emails, we can tell them what the right answer is. So a lot of times, we ourselves are good human experts. So you see these machine learning systems fail, and you're like, why is this hard? Here's why it's hard. This is what it looks like. There's no priors, there's no context. You're on a different planet, you don't speak the language, you have no idea. And you see extremely limited data, and you're asked to generalize. You're asked to make predictions about things that you've never seen before. So who wants to take a shot? Which language is that word? Klingon. Why? Why is that?
Starts with a K.
Starts with a K. Oh, but the right answer was Mlingon because it's a 3-character word. That's what was going on. Right? This is another one of those examples where there's a bunch of rules that fit. I could say that, yeah, I designed this example particularly, that it was just a 3-character word. You just never saw a 3-character Mlingon word in your training data set, but that's not the reason why it's not the case. Okay? So there's a bunch of reasons why something could be what it is. Okay. All right, so let me see. Okay, so let's do this. So we'll have to develop, so what we'll do is, let me come back to this slide. So what we'll do is we'll talk about, in supervised learning, a procedural view of things. And what we'll do is we'll differentiate between 2 phases. So if we go back to this picture of, data comes in, you choose a hypothesis class, there's a learning algorithm that searches for a mapping, that gives you a final hypothesis. We'll, in a procedural view of things, we'll talk about 2 separate sort of phases. One phase we'll call training, and the other phase we'll call testing. Okay? And the training phase is going to be exactly what that picture showed. Data comes in, and the output of the training stage is G. It's a mapping. The testing phase is when this happens. When I give you new data that you have never seen before, and I ask you to make predictions. Right? So that's the output of the testing stage is f of x. You tell me what, or g of x in this case, if you're learning g. What is f of x supposed to be? So here's one thing that's important to keep in mind. What do we want out of a good learning algorithm? What do we want out of this mapping? So do we want good performance on training data? If I give you a data set, it contains x's and y's, it would be nice, you're supposed to pick a g that somehow does well on the data set that I've given you to learn. Right? But that's not really the goal. The goal of most of these algorithms is going to be that you make predictions on data that you've never seen before. Right? So it's held out test data that is going to be the gold standard. The way to sort of, here's the way to think of training data. So x1s, y1s, that's given to us for learning this f of g. And testing data, the way to think of it is that you just see the x's, right? You don't see the y's. You make the predictions, and only for the sake of evaluation do you hand it, let's say, to an evaluation server that tells you how well you do. Okay? And this is going to be an important distinction between how we function as machine learning people in our sort of labs and research versus how you should think of this. The way you should think of your algorithms is you work for Google, you write an algorithm, it gets shipped into a product that gets sent to a phone. People take out their phone, they take a picture, and your algorithm makes a prediction whether that book cover they're holding is a novel or it's a piece of fiction, or who's the author of that book cover. Okay? You don't get to see how well your algorithm did. The user does. He either uses your thing or not, but you don't get to know what the test error of your algorithm is, because your algorithm is shipped out. Right? Of course, in practice, that's not how we can function. In practice, you need to know, I've written an algorithm, is it doing well or not? Right? I can't wait to send it out to a user, then go walk up to him, are you happy? He's not happy. Right? I need to know how well I'm doing empirically. And so, procedurally, what we'll often do, for example, in your homeworks, we'll hand you a data set, we'll ask you to split it into a test fold and a training fold. So you'll break it up into a test set and you'll break it up into a training set. You will have annotations on the test because this data set is sort of to learn from. It's a toy data set. The only use you should make of the test annotation is to compute how well you're doing on these predictions. Right? You should almost pretend that you don't have access to the test annotations. And that's why more and more modern, for example, competitions are hosted on websites where you don't have access to the test annotations. So on the homeworks, what we'll do is we'll host the homework data on this website called Kaggle. So we'll give you training data like this. So we'll give you, I believe homework 3 is like dog versus cat classification of images. We give you images, you have to tell whether it's a dog or a cat, right? So images are going to be x1 to xn, y1 to yn are going to be the labels, +1, -1, or 0, 1. And we are actually going to give you some images for which you don't have labels. And what we'll ask you to do is upload it to a website which is Kaggle, and it will tell you how well you're doing. And you're supposed to pick a good mapping based on this training data set and not use this number to fine-tune your results. And this is going to be uniform. That make sense? Okay. So the procedural view of machine learning is often, I'll write as that was on purpose. So what I'd like to do every class is take a couple of minutes around halfway through the lecture, because I've realized I run through the lecture sometimes. So I'd like to take a couple of minutes halfway through the thing. If you would like to stand up and stretch, that's fine. If you'd like to look at your notes to see if you have any questions, that's fine as well. But it's a forced break for me. So let's take a minute and I'll carry on after that.
That works perfectly.
That works perfectly.
Yeah. I just look at the clock right now. Yeah. And I want to do
Let's start. Okay, let's get started. Okay. So we're talking about the a schematic for the procedural view of machine learning, and this is what you'd implement, for example, in your homeworks. This is what it looks like. You would sort of have two phases. One of them is a training phase where raw data comes in, and there's going to be a stage called feature extraction or representation. And that is then fed into whatever learning algorithm is. And that's giving you sort of a G, right? This is your sort of training stage. That's what you get at the end of training. And at the testing stage, it's going to be this same step. Raw data comes in. There's that same box of feature extraction that gives you, usually we'll say this is going to be a vector X, or sometimes we'll say phi of X. When we want to distinguish that some information has been added or created, And what you'll do here is that same x is extracted, phi of x, and then you'll sort of classify or predict. So the output is going to be g of x, whatever.
Could you please elaborate what is phi of x?
What is what?
What is phi of x?
Sorry. So it's we're going to talk about some algorithms where you can actually do sort of data augmentation or feature augmentation. So you can actually take sort of coordinates of x and maybe combine them or sort of drop certain coordinates. So phi of x, I'm sort of treating, for all practical purposes right now, you can assume that it's the same thing as x. So it's just some representation of your data that is being fed into sort of how you're working. Okay, so let's see. It's often going to be useful that your feature extraction or whatever this representation stage is, that it's identical between the training and the testing. Otherwise, you're going to have basically a mismatch. So let me go back to that. So that was the sort of more procedural view. One view that we'll see not in today's class, but soon, is something that we'll call the statistical estimation view, which is that we won't think of these as two separate phases. What we'll try to think of is that x and y are actually random variables. That your image or your email or whatever, that's a random variable, and the label is a random variable, and they're jointly distributed. X and y are coming from some probability distribution p of x comma y. Right? There is some distribution. We don't know what that distribution is, just like we don't know what that mapping is. And the data points that you're collecting are actually samples from this joint distribution. Right? So and when you actually learn a mapping from x to y, what you're actually learning something about is that distribution. You're sort of fitting a distribution out of a space of distribution. Right? And then you have some hope of generalizing to the test set. Why should you be able to learn anything? What sort of assumptions are we making? And the assumptions sometimes what we'll make are on the family of these distributions. Okay, a couple of things. One thing, just a couple of concepts. We'll have a concept of capacity. What is the capacity to learn in this learning algorithm? That will basically be the size of this hypothesis class H. If all sorts of functions are allowed, I've erased it. If all sorts of functions from x to y are allowed, then the hypothesis class is extremely large. Then your capacity to learn is extremely large. But this is going to be a concept that will reinforce over time. Something that has a capacity to learn is a bad thing in machine learning. In life, that's a good thing if you can learn. But here, if you can learn anything, that's going to be extremely problematic. Because then we're going to have extremely few samples to train this algorithm, and then everything else will be just as likely. Okay? So capacity, we're going to search for a sweet spot in terms of capacity. Extremely low capacity models are going to be bad, extremely high capacity models are going to be bad. We're going to revisit this concept over and over again, which is the concept of overfitting. Which is this idea that we'll find a G or an F, we'll find a mapping, and it'll work excellent on training data. Right? It'll work really, really well on training data, and it'll work extremely poorly on test data. So you'll code something up on your laptop, you'll have 10 samples or 20 samples, and it'll work great. On those samples, you'll be able to predict everything. But when you move to something else, it'll perform extremely poorly. Right? And one way to do this really easily is something that you're all familiar with. It's memorization, right? You go to a class, you've seen exams for the last 10 years, you look at them, you're like, all right, I know the answers to those. You go to the exams, and if that's not the question that's asked, I have no idea what to do in this class. Okay, that's vanilla memorization, and that's what we'll open with. That's our nearest neighbor learning algorithm, which is going to do exactly that. And we're going to talk about this idea of generalization, which is the ability to achieve low error on new test data. So you search for a function G that works well, that makes predictions, that achieves low error on new data. So I'm going to talk about guarantees, and this is one thing that our field has not done a good job of producing. So there's a subset of our field which is called learning theory, which is involved with these guarantees of, okay, if you find a function that works well on your training data, what is the guarantee that it will work on a new test set? Okay, can you give me some guarantee? Here's what that guarantee usually looks like, and this is me, oversimplifying 20 years of research in this area. Here's what that guarantee looks like. If you have enough training data, and the size of your model or your hypothesis is not too complex, then probably we can generalize to unseen. These are going to be extremely weak guarantees in the sense that we're going to talk about, and this is a real word, I'm not making this up, we're going to talk about pack learning, probably approximately correct learning. And you'll notice the two hedge words there. They exist for a reason. We'll formally define them. Everything in machine learning is learning from samples. If we see a different set of samples, we'll learn something else. So probabilities can't go away. Approximately correct because we can only talk about the kinds of errors that we'll make. We will never be perfect, so we have to talk about approximately correct. So to sort of oversimplify, this is what guarantees look like. Okay, here's what I want to do. I want to show you, what I want to do is talk about how you measure performance, and I want to show you an algorithm. So I think it's about time I show you an algorithm first, and then I'll come back to how do we measure performance. So here's your first machine learning algorithm of the day, okay, of the class. This is going to be an algorithm called Nearest Neighbour, or K-Nearest Neighbour. And I'd like to do, usually when I'll introduce an algorithm, I'll have a slide like this, which is synonyms. Machine learning draws from a lot of areas, and so what you'll find is the same technique being called by different names. So you'll hear of things like instance-based learning, or memory-based learning, or exemplar methods, or non-parametric methods, or K-Nearest Neighbour. Anytime you hear those terms, what you should think about is Nearest Neighbour. So Nearest Neighbour is an extremely simple technique. It's a technique where if you want to make predictions, what you do, it's a learning technique that doesn't do any learning. Okay, if that makes any sense. Here's what it's a learning-based technique that which showed you two phases of training and testing. The training phase in Nearest Neighbour is memorization. Just take a sample and save it. Save it to memory. Take another sample, save it to memory. Because these are not people, these are machines, we can do extremely well at this task. We can save every single data point. Here's how you make a prediction. These are 4 questions that you have to answer for a family of Nearest Neighbour algorithms. Depending on how you answer, you get a couple of different algorithms. So here's what this algorithm looks like. What I'm going to do is I'm going to take your X. I'm going to go into my memory bank of other X's that I've stored. I'm going to retrieve the closest X, and I'm going to just copy the label of that X. Right? That's why I said this is a machine learning algorithm if you didn't know anything about machine learning. This is what you would implement and then realize that it's been done. Okay, so here's how you would answer this question. There are 4 sort of things that you have to specify. You have to specify how are we measuring distances. I have an X stored in my database. You give me a new test sample. How do I measure similarity or distances between them? Okay, is it just Euclidean distance? Is it some other sort of distance space? How many neighbors do I look at? Do I go and find one neighbor? Do I go and find 10 nearest neighbors? What do I do? Is there a weighting function, and then how do I fit to the local points? And I'll explain what that means. So here's the simplest. So I've answered these questions, and here's the simplest sort of algorithm that exists. It's called one nearest neighbor, which says go ahead, use Euclidean distance. This is the simplest setting of these things. Right? Use Euclidean distance. Find the one nearest neighbor you can in your data set and just copy. You don't need any weighting. You don't just predict the same output as the nearest neighbor. Right? This is about as simple as it gets. And often this is an extremely strong baseline to beat. If you write an algorithm that doesn't do better than this, then you're not doing too well, right? Because this is extremely simple to avoid. You can have a slight generalization of this. Okay, I'm not going to get one neighbor. I'm going to get k nearest neighbors. And I'm going to predict the average output of the nearest neighbors. Right? Average, depends what you mean. If it's a regression problem, then I will literally just average the y's. If it's a classification problem, then I will do majority. here's what this will often look like. So we'll have a 2D. So in this case, this is a 2D feature space. Imagine we're measuring two continuous variables x1 and x2. I ask you about this data point. Blue is one class. Let's say there's one concept and red is another concept, and I ask you what should this be, right? The closest member is blue, so you might say that label should be blue. If you expand your radius a bit, the majority of things in this are red, so you might say red. So the 3 nearest neighbor might be different. Okay, so let me show you a couple of demos of this. Actually, this one is more spectacular colors. Okay, so let's go to nearest neighbor. Okay, so let me generate some data. This is, so the axes here are x1 and x2. And let's say, this is, we are always going to be talking about high dimensional problems, but we're going to be showing you examples in low dimensional spaces because it's going to be difficult to visualize these things. Right? Let's try this one more time.
Maybe you should change the base first.
Thank you. Okay, so here's what we're looking at. Blue is one class, red is another class. Let's say you have a data set where you're measuring, each data point here is, let's say, people that do well at some sport. These guys do well, everybody else doesn't do well. And maybe this is height and weight or something. So if you're the right height and weight, you'll do excellent at the sport, otherwise don't. Okay? There are two types of things. And, I can come to you and I can ask you, okay, make a prediction about a new point that you have not seen. So here's what one nearest neighbor will do. Doesn't look big. Okay, I'm just going to 2 nearest neighbor. And here's what 2 nearest neighbor does. What it's done is at every single cell in this display, it has found 2 of the nearest neighbors, and it has done, I don't know how it decided to do majority vote in 2. But it has, if there was a unique majority, it took that color. So this entire side gets colored as pink, this entire side gets colored as blue, and I'm assuming that there are sort of equal, there is one neighbor which is blue, one which is red, and that's why this is a shade lower than that. And so this is what you would call a classification or a decision boundary. Everything on that side is labeled one class, everything on this side is labeled another class. Right? This is sort of the simplest method that is learning what one sort of class looks like versus another in this 2-dimensional feature space. And when someone was asking what sort of assumptions we make, this is implicitly making a smoothness assumption. Right? You're not writing down what assumption you're making, but the assumption here is if you look at a point X, its neighbors are probably taking the same label as X. And that's why if I poll their labels, I should be able to know what my label is. If you think about the space of all possible functions, in this 2D grid, let's discretize it, that every single pixel can take a value +1, -1, right? Every single pixel can be pink or blue. But we're not searching over the space of all such functions. Implicitly, by using nearest neighbors, we're searching over smooth functions. Right? And that's why this is sort of what we learn in quote unquote, because in this case, there's no actual learning. Does that make sense? Okay. So in spring, for example, when I taught this class, there was a really nice class project that a couple of Igor right here did, where they were using nearest neighbor. So what they did was they collected a large data set of people. I think this was your dorm. That was your dorm. So everybody in their dorm, they asked them to stand, took a Kinect sensor. The sensor gave them readings of the joints, the various joints of their body, shoulders, hips, hands, and so on. I'm assuming this is all poles normalized, otherwise it would be extremely difficult. And then what they did was they didn't look at appearance, but they just looked at the ratio of various joint distances. So what is the ratio of various the length of your leg to something else. And in that, so that was their X. And in that space, they were able to do nearest neighbor, and able to tell you that out of the 18 neighbors, nearest neighbors, 12 of them are male. Therefore, you decide that you're at least somewhat male. They make a prediction that okay. So that was one project that was done. Here's another example that I really like. This was work done at CMU a couple of years ago. I guess 8 years ago now, where they were trying to do scene completion. So this is if you think about it, this is a prediction problem that is really hard. So you go on a vacation, you took a picture, you don't like some parts of it, and so you cut those parts out. Now you'd like to fill them in with something. So here's what they did. So this is an interesting prediction problem. I'd like you to predict the label, the pixel value at that pixel. Okay? And here's what they did. I'm going to download a massive amount of data sets. So I'm just going to download pictures from Picasso that people take. And in this case, a really, really large data set. So I believe that is an image, and that's a really large data set. And then what I'm going to do is, given this image, I'm going to do some fancy schmancy computer vision, extract some features. I'm going to represent this as a vector X. And I'm going to find the top 50 nearest neighbors, or 200 in this case, from that data set. And what you find is, your neighbors sort of make sense. This was an outdoor scene. This is also an outdoor scene. There's some water. And then you sort of just do some alignment. Graphicsy stuff, we don't really care. It can be done. But after you've done that, you can sort of copy content over from that image. A little bit of smoothing, and voila, you've filled in some part of your image that you didn't like. Here's another example. Maybe you're an architecture snob that really doesn't go here. Cut it out, find a neighbor, fill it in. You went on this vacation, you were disappointed that there was construction going on, found neighbors, filled it in with something else. So this is an interesting example of nearest neighbor because what it's showing is this, the key aspect in all of this is this slide right here. The reason why nearest neighbor type methods work is if you densely sample enough, if you choose a good representation that some space that your data lives in, and if you sample that space densely enough, then you will find reasonable nearest neighbors, and you will have, because hopefully the function that you're trying to learn is smooth. It does have some smoothness in that space, and then copying over labels is a reasonable thing to do. Does that make sense? Okay, so what I'd like to do is go back to that slide that I skipped, which is sort of more mundane and procedural view of things. Let's say you make a prediction. How do we measure? How do we know how well you're doing? So we'll talk about a couple of things. We'll talk about something called a loss function. And a loss function for regression is going to be different. A loss function for classification is going to be different. But it's basically, this is what you'd like your algorithm to do well on. You'd like to have low loss. So we're going to be using this notation, and that's why it's loss functions. So let's introduce it. It's going to be a function y ground truth from a y hat, which is your prediction. It basically tells you the penalty constructing y hat when the right answer was y. Okay, that's what we'll use. We'll write this function loss of y ground truth comma y hat. Y hat is your prediction, and so that's the penalty you pay. For different problems, there are going to be different natural loss functions. So for example, if your output space is continuous, you're solving a regression problem, this will be, just take the L2 difference. So y GP minus y hat squared. So L2 loss or L2 error for regression. If you're solving a classification problem, then one common loss function is just the number of misclassifications. So for example, this is just for each data point, so L of y gt or y hat. This is a 1 if y hat is not equal to y gt, and 0 if y hat equals y gt. So this is also called the 0-1 loss. This is sort of the simplest loss function that you can do. I give you a sample, you make a prediction. If you get it exactly correct, your loss is 0, or your accuracy, if you will, is 1. Loss will be 1 minus of accuracy, and if you get it incorrect, then your loss is 1. In some domains, you're going to need different loss functions. So often, in the medical domain, people tend to reason about the kinds of mistakes that you're making. So we're going to often study this matrix of y hat and y ground truth. So let's say it's the simple case of binary classification, 0, 1. So let's say the correct label was 1 and you predicted 1. We're going to call that a true positive. Let's say the correct label was 1 and you predicted 0. We're going to call that false negative. Let's say the correct label was 0 and you predicted 0, that's going to be a true negative. And let's say the correct label was 0 and you predicted 1, that's a false positive. Right. And in different applications, there are going to be different costs for these mistakes. So notice that if we're writing losses, the loss for this might be 0 and 0. Sure, you did the right thing. The label was 0, you said 0, the label was 1, you said 1. But these two, the off diagonals, may not be equal. That's what this guy was assuming. Right? The off diagonals may be different. If you're trying to diagnose a particular disease and you make an incorrect diagnosis, whether you make the incorrect diagnosis of 0 and this person goes undiagnosed, that may be a much higher cost. So you may have to pay a cost of 10 versus if they do not have the disease and you mistakenly predict that disease, maybe all that happens is they undergo another test, which is also painful. It's a mistake, but it's not as painful as this. So you might want to say 1:10 ratio, 1:5 ratio. Okay. So we're going to talk about false positive. We're going to weigh false positive differently than false negative. That makes sense? And you can imagine as if it's a K-class problem, then this becomes a sort of K by K entire matrix of costs. Okay. For understanding how well your algorithms are doing, we will often construct what is called a confusion matrix, which is just, on the test, you try to identify what sort of mistakes is my classifier making. So you will sort of, it looks, matrix looks a lot like this, but the entries in it are not costs. The entries are what happened when I ran the data. So, things were, what sort of mistakes, how many things, what percentage, maybe the things that were zero, the things that were labeled zero, 95% of them I correctly called zero, but 5% of them I called false positive. And maybe of the positives, let's say it was like 80, 20. Right? So something like this would be a confusion matrix, where you would say, here are the kind of mistakes my classifier is making. It is making a lot of false negative mistakes, far fewer false positive mistakes. Maybe that's because it's optimizing a cost function which penalizes it for false positive. I can sort of weigh it differently and I can make different kinds of mistakes. Right? So when you actually write an algorithm, you can sort of, even in a k by k case, you can construct such a matrix and know what kind of mistakes it's making. Okay. Let me do this. Let me stop here. And next time, what we'll continue on is nearest neighbor. And what we look at are certain, problems with nearest neighbors. When do we expect it to work? When do we not expect it to work? And in particular, what happens to nearest neighbors in high dimensional spaces, where distance is important. Okay, thank you.